Can you see my slide on the screen, please?
Yes,
Great.
yes. It's visible.
Okay, so great. And I guess you can hear me perfectly, don't you?
Yes,
okay.
Of course.
Okay, so today, first, I would like to thank the organizers of this meeting for the kind invitation to present my talk today. And also, I would like to welcome all of you online attending the meeting and attending my talk. Today, I'm going to talk about a standard mathematical model for tumor growth. It is a logistic mathematical model, and the tumor model is for a animal model, and the cargo is a nano-sized system. So here is my agenda for today. I will briefly review with you the typical tumor growth models, and then I will stop a little bit longer talking about the logistic mathematical model, which is commonly used to describe the tumor growth. And then I will show you what is the animal model we are using to extract data from the breast tumor growth in Swiss mice, female Swiss mice. And then I will show you how the data were fit using the standard typical logistic model, and how we can extract information from the feeding. And then I will skip to the main conclusions of my talk. So the typical tumor growth models you can find in the literature are mainly through three types. So the first one is the exponential one. And the second one is called logistic one. And the third one is the Gompertz one. All of them describe the tumor volume as a function of time, the growth of the tumor. So typically, at the very beginning of the tumor growth, you can see the three models. They have the same trend. However, when you go further in time, so the logistic model, it tends to the asymptotic behavior of the tumor growth. So the volume reaches a final volume. And when you compare the logistic with the Gompertz model, you can see that the Gompertz goes about the same trend. However, it takes the asymptotic behavior much later on time. So this is the basic difference between logistic and Gompertz. And the first one, the exponential one, it doesn't go to a asymptotic behavior. So this exponential is typically the Malthusian growth of a population. In this case, is the population of the cells in the tumor. Okay, so let's explore a little bit more about the logistic model. So the logistic model, actually, it came from a solution of a rate equation. So it's a first order equation where it describes the rate of growth of the tumor volume. It's a first order differential equation. And you can find actually in the literature two ways to describe the logistic model. first one, you can see here, it is described as a series of a power of the volume. And so this series may contain as much as terms as you need to describe your experimental data. And the second way to describe this first order differential equation, which solution is the logistic function, is the same, actually the same exponential. However, you can describe using three parameters, which are alpha, beta, and gamma. So both ways you can use to describe a tumor growth, typically in the logistic generalized model. The first approximation of the logistic model you can find in both cases. In the first case, the first approximation is just to use the first term in the summation here. So in this case, we take just the linear term. And the same way, which means your series go up to n equals to 1, simply this. The same solution you can find if you take the three parameters in the second way to describe the differential equation. You take all of them equals to 1. So, and then here is the same first order approximation of the logistic model, where this is the standard or first order logistic model. And you can take, for instance, the volume, the tumor volume at the very beginning, t time equals to 0, equals to V naught, and the tumor volume at the asymptotic position is the maximum tumor volume we call a carrying capacity. And then here is the solution. So you can see this function includes an exponential term. And if you look at the plot on the right-hand side of my slide, this is the typical plot of the first approximation of the logistic mathematical model. Is a tumor volume versus a time. So the typical curve is the solid blue solid line. And I have two interesting points to remind you here. So first, the asymptotic volume is what we call the carrying capacity, is the constant C in the differential equation here. And it appears in the solution of this differential equation. So at half tumor volume, half maximum tumor volume, you have an inflection of the standard curve. So this is the inflection point, which means inflection here. So the derivative is negative above the inflection time, and below the inflection time, the rate of curve is positive. So it goes with a positive rate and then invert to a negative rate. So the data I'm going to show you today, it was fitted with these first approximation of the logistic model. So here is the animal model we use. We use female aged mice, and we implant tumors in this female. We implanted in the breast of the female mice. And besides implanting the tumor, we started the treatment of the animals 2 days after the implantation of the tumor. And the treatment includes a nano capsule of PLGA, And inside this nanocapsule, we could include magnetic nanoparticles coated with citrate, and also we could include cellulose. I will tell you briefly about cellulose, my next slide. And then we started treatment of the animals using injection of a suspension containing these nanocapsules, including cellulose and magnetic nanoparticles. And then in some groups, selected groups of the animals, we performed magnetohyperthermia, and then we follow the tumor growth as a function of time. Actually, we selected 8 animal groups. And let me tell you a little bit about selenium, the cellulose. Actually, cellulose is a selenium organometallic. It's about 5% selenium organometallic. So it includes about 5% of selenium in this organometallic. So there are different ways that selenium can appear in this molecule. So I just show you a few of them. So in this slide, you can see, so this is a triglyceride actually, and it includes cellulose in one chain. It could be this kind of structure in the cellulose. You can see 2 hydroxyl groups or only 1 hydroxyl group next to the cellulose, or no hydroxy group next to cellulose site. And we may have also this structure here, cellulose in this configuration, and cellulose in this and selenium in this configuration. Okay, so what is about cellulose? Cellulose, it's a well-known cancer prevention, and it has been used for cancer treatment. Actually, it's antioxidant molecule. In some cases, it could work as a pro-oxidant molecule, actually. Okay, so here is the design of the experiment. So we selected 8 groups, 7 animals in each group. So they are all aged females, and the age has a very interesting aspect. We want to know how one aged population can react to a treatment of breast tumor cancer. And so this research is addressed to extract information for further development of drugs for old females. So the tumor were implanted at day 0, and then we wait 2 days to start the treatment. And the treatment follow up to day 13. So we perform different treatments. First, the first animal group was the health group, health animals, no implantation of tumor. And the last group, animal group, was implanted, and it was treated with a standard chemotherapy agent, which is Plaxitel. So this is a control group in terms of the animal planning. And we have animals without implanted with tumor and without any treatment, and animals which were treated with magnetic nanoparticles only, cellulose nanocapsules only, performing magnetic hyperthermia with animals taking cellulose nanocapsules, performing treatment injecting magnetic nanoparticles and cellulose nanocapsules. So it's important to mention that magnetic hyperthermia treatment is performed with nanocapsules, including cellulose and magnetic nanoparticles. So after selecting all these groups, I can show you how was the time evolution of the tumor volume? We can see in this plot, so the tumor volume as a function of time up to day 13, and symbols are the experimental data, obviously. And the solid lines are the best fitting of the solution of this first approximation of the logistic model. So from this fitting, of course, we can extract important information about the different treatments. But you can see here in this plot that on the right-hand side, we take the tumor volume at the last day of treatment, day 13. And you can see that the magnetic, the animals which were treated with only cellular nanocapsules, which mean nanocapsules containing cellular, they reach the minimum final volume. And then those animals treated with cellular nanocapsules plus magnetic hyperthermia, they also reach a very small final volume compared to the other ones. So the third in sequence was the animals treated with magnet nanoparticles and cellular nanocapsules. It's important to point out that animals that receive the standard chemotherapy treatment, so they came out with a final tumor volume just around average between all animal groups. Okay, so I can collect in this table the important points. So K is a typical constant that is related to the growth rate of the tumor volume. And C is the carrying capacity, which means the final volume of the tumor growth. So it is the asymptotic value of the tumor. V naught is the initial volume, which was fitted. And Ti is the inversion time, which means the time that the growth of the tumor invert from a positive derivative to a negative derivative. So it's a very important parameter here. The sooner the tumor volume invert the growth rate from positive to negative, the more effective the treatment is, actually. So if you compare all groups, that it is not included here, of course, the health animals group. So we only include 7 groups. We exclude the health animals from here because we don't have tumor to measure volume in the animals. So the health group was not implanted tumor in the female mice. Okay, so finally you can see, if you look at the parameters, you can see that the shortest inversion time is exactly, which is about 5.4 days. It is exactly with the animals that receive magnetic hyperthermia treatment with cellular nanocapsules. Of course, cellular nanocapsules here containing cellular and magnetic nanoparticles. So if you compare this data with animals treated with only cellular nanocapsule or magnetic nanoparticles included in cellular nanocapsule without magnetic hyperthermia, you can see that the data are much better in the case of performing magnetic hyperthermia. So this is a very important point that signals the synergies of magnetic hyperthermia and treatment involving cellular nanocapsules, including magnetic nanoparticles. So this gives us some hope that there is a very interesting synergies between the application of magnetic hyperthermia and using nanocapsules, PLGA nanocapsules, including silol. So this is a very interesting data. Although we didn't have any complete remission of tumors, but this treatment was able to block the tumor grow and block the tumor grow more efficiently when we are combining magnetic hyperthermia with including silol in a PLGA nanocapsules. So this, if you want to see more details about this work, you can find the publication in 2022 in Nanotechnology. So more data are included in this paper. So I want to come to my main conclusions to do this talk. And the first point is that this treatment, it provides outcomes actually with reduced dose of both silol and magnetic nanoparticles. Plus, it included considered a short treatment time of just 1 week treatment time. Second important point, no metastasis and no side effects were observed in the best treatment that I show you in the table, which is the magnetic hyperthermia plus silol nanocapsules. Third, the measure of tumor volume, which was measured by caliper, and the carrying capacity, the data are very much consistent. So you can see from the standard deviation of the parameters we can extract from the fittings. And one more important point is that the first approximation of the logistic model describe, at least in this experiment, describe successfully the tumor growth. And one more, the observed synergic effect. This is a very important point. It's obvious the synergistic effect when we combine silol, which is a new adjuvant, and magnetic hyperthermia treatment. And finally, so the combination of magnetic hyperthermia and silol nanocapsules, of course, including silol and magnetic nanoparticles, is very effective and safe to block the tumor growth in aged animals. So these are the main conclusions of my presentation. And I would like to, again, to thanks